So we see your slides, Ruth. Are you ready to start?
Yes.
All right, it's a true pleasure to introduce Ruth Britto from Trinity College in Dublin, who will tell us all about the coaction for Feynman integrals. So take it away, Ruth.
Okay, thanks. Yeah, thanks very much for having me here. I'd like to present some work that was in progress for a few years, but we finally completed a paper earlier this year. This is in collaboration with Samuel Abreu, Claude Dürr, Énan Gardy, and James Matthew. So the overview is we've been looking at these coactions on Feynman integrals from 3 points of view. And so we formulate 3 coactions that are all mutually compatible. The first is what we now call the local coaction. And this is actually adopting the terminology of Brown and Dupont, local coaction on multiple polylogarithms. So this is the best known one. This is the one that is familiar from the work of Goncharov and Brown from years ago. So it's well known in multiple polylogarithms, has been used to great effect in computing Feynman integrals, and has been generalized to elliptic multiple polylogarithms, and I guess other similar structures of iterated integrals. So this you can apply to Feynman integrals when you compute them in dimensional regularization and then perform the expansion in the dim-reg parameter epsilon. The next version of the coaction we call, again following Brown and Dupont, the global coaction. This is an operation on generalized hypergeometric functions. So this applies to Feynman, the same Feynman integrals in dim-reg, but now without taking the Laurent expansion. So it's known in the examples where you can actually arrive at a closed form, that they are expressible in terms of generalized hypergeometric functions. So this global action is conjectured now to exist on the hypergeometric functions, and this was conjectured based on actually what's coming next, the diagrammatic coaction related to the first coaction. So we conjectured that this exists for arbitrary Feynman integrals in dim-reg. We found several examples with integer-based parameters that arise from Feynman integrals at one loop to begin with. And since then, this global action has been proved for Laricella functions by Brown and Dupont in a very mathematically rigorous way. Okay, the third one is this diagrammatic coaction. And this builds upon these 2 coactions. So when we say, right, so these are meant to be mutually compatible. So it's a coaction that means you can evaluate, you can expand and then take the coaction, or alternatively, the operations commute, right? You can take the coaction of hypergeometric functions and then polylogarithms, and then to the expansion, or do the expansion first, take the coaction, arriving at the same result. This will probably become clearer when I show an example shortly. But then they're unified in the context of Feynman integrals and their associated graphs. So the first claim is that the coaction output from a Feynman integral, when you evaluate it according to the Feynman rules and then take either the local or the global coaction, the first claim is that that can be that expression of functions that you get from taking the coaction can be repackaged in terms of Feynman integrals, and notably also cuts of Feynman integrals. So the second claim then is that the coaction output can not only be repackaged, but that what you obtain by the repackaging can also be obtained by applying graphical operations to the diagrams before evaluating. And these kinds of graphical operations will involve pinches and cuts of the graphs, or the propagators. So a few remarks as we begin. The coaction is naturally compatible with taking discontinuities and differential operators. This will be very familiar for people working on the symbol calculus, so we hope it can be applied to new computations to great effect. For us, dimensional regularization is absolutely essential because divergences exist. Even if you start with an integral that's finite. By the time you apply cuts and pinches, you'll be involving divergent integrals. So this is all within this context, definitely. I should mention that formally, if you're really doing the mathematics properly, you have to distinguish motivic and de Rham, multiple polylogs, hypergeometric functions, etc., or use single valued versions. And for the sake of this brief talk, I'll be glossing over that distinction entirely, but it is important. So in this talk, I want to discuss the general principles we've found and show 1 and 2 loop examples, especially focusing on the 2 loop examples because that's what's new for us. Okay, so here's a starting example to bring this to life. And those of you who've seen my talks on diagrammatic coaction before will probably recognize this example. So this is a simple Feynman integral. What we have to say when we're evaluating it is, besides just showing a diagram, we'll specify that we mean a scalar Feynman integral, and that we have to specify what dimension we're evaluating it in. So let's say 4 minus 2 epsilon. Okay, so given that, you can evaluate according to the Feynman rules, and you obtain this closed form expression, which does involve this hypergeometric function, in this case, the classic Gauss 2f1. And then you can expand it in epsilon. And here you see there is an IR divergence in this integral, and then there are some finite terms, and you might stop there, or you can compute higher orders if you wish. Okay, so now we propose there are 3 compatible coactions, which means we can take a version of the coaction on each of these 3 expressions. And so now I'm assuming that most of the audience here has at least a superficial understanding of what I mean by coaction, because I'm not introducing that properly. But just for a few of you who might be here who are not familiar with coaction, let me just say very briefly, coaction, to understand it, first think of a co-product as a dual version of multiplication. So this prefix co in mathematics and algebra means that you take your axioms of, say, multiplication, you write them all in terms of maps and diagrams with arrows. So you have like 2 copies of a space going to 1 copy of a space for multiplication. And this co-construction means you have an operation where all the arrows in the definitions and the axioms will be reversed. So co-multiplication goes from 1 copy of the space to 2 copies of the space. So here is, for example, are some examples of the coaction on logarithms and the dilogarithms. So this is what this tensor product is doing here. We're going to 2 copies. And then, okay, why it's a coaction and not a co-product? That's because the operation that we're reversing the arrows of is not just multiplication within a ring, but with a ring and a module. So you have actually 2 separate spaces, and that comes back to that mathematical distinction. Okay, so here, this is the coaction on polylogs that you can apply to this expression. Fine, that's the well-known version. Then another one is this one, a coaction on the 2f1, a hypergeometric function. And actually, in this talk, I won't be explaining at all where this comes from. I did go into some details of this at Amplitudes last year. But anyway, here's the result for 2f1. So again, you have 2f1. This one is written in terms of 2 terms. We have 2f1s on both sides of this tensor product. So the first claim, right, is that these are compatible, that if you take the coaction of this expression and the coaction of this expression, and then take the Laurent series expansion of the hypergeometric version, that you would land on the coaction you computed here. Okay, then there's the third one, which is the coaction on diagrams. So here, remember, this is going to involve pinches and cuts. So again, we have the tensor product and the coaction. and we have diagrams on both sides. And here at one loop, yes, we can understand exactly how to predict what shows up here on the right-hand side. Here in the first entry of the coaction, meaning before the tensor product, we get integrals related by pinching propagators of the original integral. And in the second entry on the right side of the tensor product, we get the original integral where certain propagators have been cut. Okay, so then again, the statement that this is compatible is that we can take these diagrammatic operations, and the reason we say this is a sensible thing to do is not only that it obeys the axioms of a coaction, but also that when you evaluate all these diagrams according to the Feynman rules and according to our understanding of cuts in the Feynman rules, that then again you would derive the same expressions as if you took the coaction here or here. So here we're going to focus on the two loop example. So here's just a preview of what one of those will look like. So this is for a sunset with two massive propagators. And just to see, we'll see the same kind of structure as at one loop, where in the first entry we have integrals or graphs related by contracting propagators. And on the right side, we have various cuts of the original integral. Now, one new feature here at two loops is that because you can have multiple integrals in the same topology, we'll have these extra labels like here 1 and 2, referring to the fact there are two master integrals in the top topology. So see, this one is not any kind of contraction. It has the same topology, but we do need to involve the second master integral. And we have this general formula, which we call the master formula for coactions on integrals. And this will apply actually to all three versions. So if you take the coaction of an integral, you understand that when you define an integral, this omega, this form that's being integrated, that's an element of some cohomology. And here gamma, the integration contour, that's some element of some homology. And in the coaction, you introduce a sum over some generators of cohomology and some, well, dual, if you like, basis of homology, and you insert this basis on the right side, and that's what you will get for the coaction. So now I'll take some time to discuss the properties of this formula, and then we'll see how it applies to our three coactions. So here, again, all three coactions have this structure. We note that this construction satisfies the axioms of a coaction. And the statement really here is that for the cases we're going to look at, that there exist some sets of generators of homology or elements of cohomology, homology, and some rational coefficients that will make this formula true. So these omega I will be the generators of cohomology, the gamma j's will be the generators of homology. These, I should say, are rational in epsilon. They can be algebraic in the kinematic variables. And based on our choice of the bases of homology and cohomology, we will fix these coefficients, and we might find it convenient then also to rotate the basis, to diagonalize the matrix so that we arrive at the form given here, which is just a bit cleaner, but doesn't really have any additional requirements. Okay, so how are we going to choose these bases of cohomology and homology? So here on the left entry, the first entries of the coaction on the left, where we're changing the integrands, these integrals are going to be related to the original integral we're looking at by standard IBP reduction on Feynman integrals. And we'll make a selection, we choose them to be pure just for convenience. By the way, we can also establish how many generators we need. Okay, so I mean, IBP reduction, if you have an algorithm for that, that will just work. But you can also try to select some forms that you like, and then it might help to know the dimensionality of a homology. And of course, we know that we can compute that based on counting the number of critical points of the graph polynomial u plus f under suitable conditions. On the right here we have integrals that are related to the original integral just by a change of contour. So how do we do that? Well, we have understood that when you change the integration contour of a Feynman integral, that is one way that you arrive at cuts, or the definition of cuts is taking certain residues, which can be described by changing the contour. So how do we select our basis? Well, we could imagine taking all possible cuts, all possible combinations of propagators being cut, but that's too many. There are many relations among the cuts. And these are analogous to the IBP relations because we know the dimensionalities of cohomology and homology should agree. Here's one important relation that we found previously for one loop integrals, which is a linear relation between an uncut integral and the sum of all its one line and two line cuts. Now this is definitely in dim-reg, the epsilon is involved here. It also is, whenever we compute cuts, actually in this context, we're computing them modulo I pi. And this is related to having two different spaces in the coaction. And the fact that in the coaction, as we understand it in this context, that all the elements here are only taken modulo I pi. So this is fine because this is going to be used on the right side of the coaction. Now this is a lovely relation, and it's only true for one loop integrals as such, but we can use it as applied to subgraphs of multi-loop graphs if we integrate loop by loop. And based on that consideration, we arrive at the principle that we don't need any, as we're trying to reduce the number of possible generalized cuts that we're considering here, we don't need to consider any generalized cuts in which there's any completely uncut loop. Because if you had any subgraph that was completely uncut, you could use this relation to exchange it with graphs in which at least one line is cut. So we'll restrict our attention, at least to what we call genuine L-loop cuts. It means that you can't find any loop that's totally uncut. Okay, so here, this is what I mentioned a moment ago, that if you would like to arrive at the compact version of the master formula, where you only have one summation index, where you have omega I that's somehow dual to a contour. So one way you can get this, of course, is just choose any basis and then diagonalize the matrix and rotate your bases accordingly. But so formally, but you can also try to get it directly. Now, formally, there is no such duality that's really established for motivic integrals, but we can aim for this form and try, given a basis here that we might get by IBP, we'll try to define these cuts accordingly. And so the way you might try to get this form directly, if you like, is to find the bases omega I and gamma j such that this condition is satisfied. So that, see, we're changing the integral around now. Now we're integrating our basis elements in cohomology over the basis elements in homology, and would require that we get the identity matrix plus higher order terms. So to get this, form, this duality, actually, because we're looking at pure integrals, that means this is not just higher order in epsilon, but this is includes all our transcendental functions. Includes only transcendental functions. So what this is saying now in terms of Feynman integrals is that gamma I, the one that's dual here, should take the residues at all the poles of omega I. That is to say, if a propagator exists here, then it is also cut here. So we understand this very well at one loop, and we use this as a guide at two loops, I should say. So at two loops, we have not arrived to the point where we have full control of describing the coaction, and we'll see that in the example. So we can, because there's still some freedom in specifying the exact contours. Okay, so to summarize, as we're looking for the diagrammatic coaction, the integrals here on the left are related by IBP, and we only have L loop diagrams because that's all you can't reduce the loop order by IBP relations. On the right side, you have genuine L loop cuts. We know the coefficients very explicitly at one loop. For higher loop examples, they're ad hoc. So I'll show examples where we don't have the coefficients. You won't see these coefficients appearing, but that's just because I've absorbed them into the definitions of the contours. But that's something we do ad hoc. We can dualize the bases either before or after making the initial choice here. And one thing to note is that they are consistent with degenerate limits, which is not obvious either from the mathematical point of view or the Feynman integrals. So I should say, this is just something we've checked in examples. This is something we can't quite prove, but it's looking good. And by degenerate limits, I mean that Mandelstam variables are going to zero or becoming equal to other ones or to the external momenta. We have a mechanism by which the UV and IR poles cancel. These appear generically when you pinch propagators. Gamma now itself, I've been talking about starting from ordinary Feynman integrals, but in this form, let me just comment that you could, since this is quite a general formula, you could start with a gamma here that's not the uncut contour, but it is actually a cut contour, which means we directly already have a coaction on cut integrals. Or said differently, you can take a formula and then you can apply a cut to the whole formula, and that will act on the first entries here. Okay, so now we're ready to look at the examples and see how this works at two loops. Our first two loop example will be one mass sunset. So here we have two master integrals. We've chosen some normalization factors so that they're pure and start with the 1 plus higher order terms. They are both in 2 minus 2 epsilon dimensions for purity. And what else? Here's a factor from showing the dimensionality from dim reg. Right, so this is a rational factor that has the effect of making, well, yeah, this is the rational factor such that the rest of the expression is pure. We have here just 1, 2f1 in each of these integrals. So we know that 2f1, this hypergeometric function, has a second order differential equation. So the fact that there are two solutions to the differential equation corresponds exactly to the fact that we have two master integrals here in the top topology. These are essentially generators of this space of 2f1s. Okay, so now we have our basis of integrands. So the integrands have been specified here. So this is, say, your ordinary starting scalar sunset, and then the second one we've defined by inserting a numerator. Okay, now what about the cuts? There are only two independent master integrals. So there are also only two independent cuts, and we can take those to be the two maximal cuts. So let me show this a bit more explicitly here. If you consider the maximal cut, so you put all these three propagators on shell and start taking the residues. After taking three residues, you still have one integration left over this variable. And you can see directly this, if you know the integral representation of 2f1, you'll recognize it here. So for this 2f1 now, but when we take these cuts, by the time, since we're just taking residues, it's not, we don't clearly have a definite choice to make for the integration contour here. So this is why we can choose our two independent contours and arrive at two notions of a maximal cut, right? So only one will correspond to one combination will correspond to what we understand as the physical discontinuity. Okay, but we have two independent contours. And one way to understand this is just to integrate between different pairs of branch points. So if you do that here, we arrive at these two results. So these are now two independent maximal cuts. And again, we see our same two F1s returning, which belong to the same space. So now, if we would like to arrive at the compact form for the coaction directly, we would like to impose this condition. Remember, so we have our two integrands, we have two contours, and so these contours are defined as capital gammas here. So now to rotate to the dual form has the small gammas. So again, this is what we say, we just do it, we rotate the basis such that we impose this condition. So these are the linear combinations of those contours that satisfy this relation. And that allows us then to write down the coaction in a very clean form here, which is what we can write as a formula. So here we have the two different topologies in the first entry and the two independent maximal cuts in the second entry. And here it is in terms of pictures. So we can check agreement with the coaction on 2f1. And so now for these two loop examples, I said we really emphasize the coaction on the hypergeometric functions rather than on the multiple polylogs because it's a closed form. So then, especially if we're trying to fix the coefficients, we don't have to worry that something strange is happening at higher orders. It's all right there. So all the examples we've worked through have been in terms of the hypergeometric functions. Okay, so let's look at these pictures. I'll be showing more pictures lately, so let's make sure, shortly, so let's make sure we understand what these pictures are, the notation of these pictures. Right, so we have 1 and 2 for the two master integrals, meaning the two integrands. And now these lines here are, the dashed lines for cuts are color coded so that the red dashed line is dual to the red one and the blue dashed line is dual to 2. That's what that means. So we see, you can check that it corresponds exactly to what this formula is, right? So in the first entry, the contour is the same, nothing's being cut. In the second entry, you do have the dual contours to the integrand. So this 2 goes with the blue, 2 goes with the blue, 1 goes with the red here, and so on. And this label is inherited here, and same for here and here. Okay, so some comments. Remember, so we do just have a two-dimensional space of homology. So that includes in particular the uncut contour. So there is, I haven't worked out these coefficients, but they exist. You can, and in any other cut you might like. So this purple line here represents some general contour. It's not necessarily a maximal cut. It could be any cut, including an uncut, a non-cut. Those are all linear combinations there. Again, in terms of these two maximal cuts, you can recover the discontinuities in the two kinematic variables. And so again, for this general cut, you can take the coaction of a general cut or integrate it over general contour. This is just a pictorial version of changing the initial integration contour here to an arbitrary one in this space. Okay, so let's move on to the remaining examples we've worked out. Here, this is quite a simple one. This is just a double tadpole, so it's just a power function. I mean, this is really just follows directly from the one loop result, just from this basic property of a coaction that coproduct commutes with multiplication. Okay, of course, much less trivially, then we come to the two mass sunset. So now we've got three integrals, three masters in the top topology, and the fourth master is the one I just showed, the double tadpole. These expressions, when you integrate them, they involve the appel F4. And for a basis of cuts, we have, just as there are three master integrals in the top topology, there are three independent maximal cuts. And then there's the fourth master integral. So there's a fourth cut, which is not maximal. So we choose one line cut, one two-line cut that is the maximal cut of that double tadpole to complete our basis. So these are all computed in terms of the appel F4. And we had to choose some representations of appel F4 that correspond to the result of our global coaction. So if you are doing this in practice, it can involve some manipulation of identities of hypergeometric functions. So this is the result. This is now similar to what we've seen in the other examples. So we can see, just as for one loop coactions, now we see we have the terms related by pinching propagators, as well as all the masters and their dual cuts. And we have, right, so I mean, I haven't fully reviewed the one loop coaction, but just as at the one loop coaction, when you pinched propagators, you could get what we call the deformation terms. So see, all these ones in the top topology, they come out with just one term with their dual cut. But when in the lower topologies, you have linear combinations of all the cuts appearing. And so this corresponds to, or the same line as what we saw at one loop. Okay, our next example is this double-edged triangle. So here we have two master integrals in the top topology and two other ones, which are zero mass sunsets. So again, the maximal cuts, these two three-line cuts appear only along with the sunsets, and they go along with deformation terms like this. So again, we have used some of the freedom in the definition of cuts to fix them, so the coaction takes this nice form. I'll show briefly that how we take degenerate limits. So imagine we have, in this example, we'd like to consider the limit in which, say, this line here is becoming massless, p2 squared is going to 0. So in that case, our space of master integrals collapses to only two. We have one in the top topology and one sunset. So now in terms of these new masters, we need to construct new dual integration contours. So you can do that as such, and you can obtain the coaction either by taking the limit of the one on the previous page or directly with this dual basis as shown here. There's another degenerate limit to consider. So we've considered several degenerate limits, and maybe not, perhaps not all possible ones, but many. So if we take, on the other hand, this line over here becoming null, then the integral is reducible fully to just the two sunsets. So there are actually two master integrals, and these are them. And so the fact that it's reducible now is reflected in the fact that the 4-line cuts are not showing up here at all, because those are 0, and they're also just not needed diagrammatically, as you can see here. All right, just a couple more examples. So here's one with adjacent triangles. So this involves now the 2F1, also a 3F2 appearing twice, and there are 6 master integrals. And there's only one in the top topology. All the other 5 are quite a bit simpler.
About 5 minutes left.
Great, thanks. And here, yeah, so this is an example you might have seen me show before. This is very nice because here none of the cuts need any additional colors. Because we've got different topologies, this is extremely clean. So we have really precisely every propagator that shows up on the left of the coaction is being cut in the corresponding right entry. That's all it is. And here we've also carried out a careful check of a degenerate limit where one of these masses go to 0, which is actually, I mean, even though this is a very clean coaction, there are quite some subtleties involved in checking that, but it is all consistent with the naive application of the diagrammatic coaction. And one more example that we've worked out is this diagonal box. So here we have 2 2F1s, but they are related. So you get a space of 3 master integrals, as shown here. So the original topology then and 2 contractions. And this similarly is clean like the previous example because of the separate topologies. And another nice thing here is that the cuts that appear are exactly just the S channel and T channel cuts and the maximal cut. So those are very natural cuts appearing on the right of this example. So to summarize this, we've conjectured that this diagrammatic coaction exists, which is compatible with a local coaction on multiple polylogs and related functions, and also with a global coaction on hypergeometric functions, which in turn is conjectural. We have a very clear conjecture at one loop. Beyond one loop, we have actually just these examples, but we lack a precise prediction because, as I mentioned, the rational coefficients that turn up are being hidden away in the definition of the contours. But we do have some principles that will guide us going forward, and especially looking at more complicated types of functions. And most notably, our principles are that the coaction of the L-loop graph should have L-loop master integrals in the left entries and genuine L-loop cuts in the right entries, and exhibits a pairing between these objects. And propagators that appear on the left we expect to be cut on the right, and additional propagators could also be cut on the right. Anticipating a question about elliptic examples, we're not ready to formulate a global coaction on hypergeometric functions that would have expansions in terms of elliptic functions, or said differently, that are expanded around non-integer parameters. But we have started to look at the diagrammatic version, at least the elliptic sunrise, and I'm ready to say confidently the equal mass sunrise looks good. Even the unequal mass sunrise is not complete, but I think there's no reason that that wouldn't work either in terms of checking with a coaction on elliptical multiple poly logarithms. All right, I'll close there and open it up to questions. Thanks for your attention.
That's all. Thank Ruth. So I see that there is a question from David right away.
Yes, well, congratulations on these very explicit two-loop examples. My question concerns the double-edged triangle. There was a paper by Dirk Kreimer in May who defines a coaction on diagrams based on the cubical chain complex, which he says is completely compatible with what you do for diagrams that reduce to multiple polylogarithms and for simple graphs like the sunrise diagram, where the number of spanning trees is the number of edges. But he explicitly says that the what he calls the dunce's cap, and you call the double-edged triangle, and I call the ice cream cone, generic kinematics, that there are problems for a coaction on that graph. Do you have any understanding of what the problem might be?
No, I do remember that paper, and I should remember. I think that they're still not in dim reg though, right? So that's. I think with the general kinematics, everything should be finite, and then it's. No, okay, so right, I haven't understand. It was encouraging that I think he sees some agreement, but I think the way he formulates it, if it's not in dim reg, then I wouldn't understand how to make that correspondence, and I haven't been able to understand much of that paper, I'm afraid.
I had exactly that problem in understanding the relationship between his work and yours, but it was encouraging that he underwrote all of the examples you've done and shown that very explicitly in dim reg. So that is encouraging.
Yes. So yes, their work does seem to be moving slightly closer to the direction we're going as well. So we'll see.
Agreed.
Then we have a question from Lance.
Hi, Ruth. Thanks a lot for a great talk. I have a question about something you said at the beginning. Well, also just now about dimensional regularization being crucial, but more specifically, you said that if I take the coaction according to these rules, then the things on the right-hand side might be singular in dim reg, even if the thing on the left was not. And I mean, there are lots of examples of finite integrals in d = 4 that are polylogs, like the ladder integrals of David and generalizations of them and fishnets and things like that. And if you just hand those functions as iterated integrals to a mathematician and tell them to take the Brown-Goncharov coaction, it will be finite, right?
Oh, I see. That's right. Because sure,
so
yes. If your integral is finite, yes, then its coaction will also be finite, right? So what we have is in our operations, of course, we arrive at divergent integrals, and then of course the divergences have to cancel. So okay, yes, the way I'm formulating it,
would you have divergences? Would you have divergences on the right-hand side in individual terms in your coaction?
Individual terms? No, that's right. But yes, if you do start with a fully finite integral, then of course its coaction should have an expression that does not involve divergences, but that I wouldn't know how to get there directly.
So do you think your rules would produce things that are finite in those cases? Or
oh yes, no, that's it, because we have some mechanisms by which these poles cancel.
Do they cancel between terms, or do they cancel?
Terms, yes.
But then I still don't understand how your coaction is compatible with what I think was the first coaction that you defined, because that one's sort of manifestly finite because you don't even see epsilon at all.
Well, the divergences cancel. then you can take epsilon to 0 after they cancel.
So they, okay, they cancel among different diagrams, but within
it's also very
terms,
much related to
terms
this,
in the coaction on iterated integrals, or the original coaction.
this relation that we like, right, which we secretly call the pole cancellation identity,
Oh, okay,
but we don't call it that in public because that would be too confusing. But
okay.
this is what it does.
So anyway, that means that that's how you get compatibility with the fact that a finite coaction on a finite integral is finite.
Mm-hmm.
Okay. Thanks.
So that brings us to the mark for the short break. So maybe we should thank Ruth again, and then we can continue also the discussion after the recording ends, if anybody's up for it.